Welcome. This presentation covers the modernizing reports for the Mexican Space Agency (AEM) on how the project satellite data using distributed systems infrastructure developed in collaboration with Noaa by Samuel Armas, Víctor Morales, Itzel Ramírez, and Ángel de Jesús Torres. The Mexican Space Agency AEM is responsible for leading Mexico's advancement in space science and technology. Its mission is to position Mexico as a leading nation in the global space industry. AEM operation trunkified coordination trained of human capacity sizing respecting industrial development, international affairs, and financing and information managing. This last coordinationally is the one or project direct impacts and modern needs. Now, the problem IEM current infrastructure relies on the singles centralized server to receive satellite data from NOAA 19. This creates what engineers call a single point of failure or SPOF. Here is the critical risk if the server fails, due to power out, the saturation, or physical demand. All data reception stops immediately, and because temporality files are stored localization before any backup, the data loss is permanent and irreversible. There is also a scaling problem, vertical scaling, adding more capacity to a single machine as a hard physical sailing onset that sailing is reached, the survey can no longer handle the incoming satellite file and disconnect entirely from NOAA 19. This means ITM is one hardware insanity always from complete loss of sizing date. There is no redundancy, no backup path, and no way to recover what is lost. When servers fail to completely sizing stop page, this is the missional critical rig or project was bought to eliminate.
Our solution works at two levels. The first is intra-node protection. Protection inside each individual storage node achieved through a RAID 50 configuration RAID 50. Combines RAID 5 with provides distributed parity for fault tolerance with RAID 0, which use block stripping for maximum write performance. In practice, this means the system survives the failure of one disk per write 5, set with 0 data lost. At the same time, write 0 stripping maximizes write speeds, which is essential for continuously ingesting satellite data streams for NOAA 19. The minimum hardware requirement is 6 writes per physical node. The result at the micro level continuous operations even when a physical disk is missing. Zero data loss warranted at the node level. RI-50 protects each node individually, but what protects the entire cluster? That is when SEP comes in. SEP is an open source distributed storage system designed for cluster wide resilience, running on standard commodity hardware. The core of SEP is a closed algorithm, controlled replication under scale hastening. Cluj distributes data evenly across all nodes with no centralized bottlenecks. Any node can independently calculate where any piece of data lives, no master directory, no single point of failure. When a node fails, SEP automatically redistributes the data replicates to the survival nodes with zero humans intervention. All nodes stay in SIX through the current protocol, ensuring every copy is identical and verified. Strong consistency, automatic self-healing, no central bottleneck. This is the backbone of our distributed infrastructure. Let's now see how both layers come together in the full proposed architecture. A dual layer pipeline that takes Satellites data from the moment it arrives at the way to fully replicate distributed storage. Layer 1 is reception. The AEN main server running Linux receives APT data directly from Noaa 19, a Python ingestion agent watches the files system in real time and triggers replication the instant a file is ready. Layer 2 is distribution, a set-powered cluster of four independent nodes, each protected by RAID 15, receives the data simultaneously across the nodes at once. And two layers for nodes, zero single point of failure.
The architecture relies on four core components, each operating independently so that no single failure can bring the system down. First, the AEM main server, the Linux based entry point for all satellite data. Second, the injection agent, a Python based engine that monitors the file system and triggers replications automatically. Third, the subcluster for this decentralized nodes with self-healing data integrity verifications. And first, the RAID 50 layer hardware level protections inside each node, ensuring fault tolerance and fast RAID performance. Each of the four nodes operates as a self-object storage daemon or OSD with its RAID 50 protection oriented. Every satellite dataset is stored using a triple replication factor, meaning three identical copies existed simultaneously on three different physical nodes. This gives the system N plus 2 resilience. Full data accessibility is maintained even if two complete nodes fail at the same time. That is the maximum tolerable simultaneous failure scenario. Three copies for nodes, the cluster self chills and maintains strong consistency at all times. A key component of the system is water, a fully autonomous surveillance service that runs 24 hours a day, 7 days a week, 365 days a year. Unlike traditional systems that check for files schedule, the water reacts to fail system events in real time. It triggers the instant a file is detected, and more importantly, it identifies the exact moment a file finishes writing before sending it. This prevents any incomplete or corrupted data from entering the cluster. The result is lightweight Python-based agent that runs continuously. No manual check-ins, no human fatigue, no missed files. Once the water triggers replication, a three-step protocol takes over. Step 1. Parallel transfer files are sent to all four nets at the same time, maximizing bandwidth and minimizing delivery time. Um, Step 2. Quorum verification. The process only completes. Again, the majority of nodes confirm they hold a identical verified copy. No person writes, no corrupt states allowed. Step 3. Autocorrection. Safe uses checksums to detect any transfer error and automatically pulls clean data from a jealousy node to fix it. Um, Zero human involvement at any step.
We validate the systems against all four critical failure scenarios. It could it could realistically face, and in every case the result was the same: zero data loss. Um, Scenario one: a single disk fails inside a node write 50, absorbs the failure transparently. The node stays fully online with no interruption to the data processing. Okay. Um, Scenario two: one complaint node goes offline. CEPH detects it and redistributes replicas automatically across the remaining nodes. No human action needed. Scenario 3: two nodes fail at the same time. The for 3 replication factor keeps all data fully accessible across the surviving nodes. Scenario 4: a node is isolated from the network's CEPH, marks in it as a down and redistributes its workload instantly for scenarios, zero data loss every time. In terms of performance, the system achieves full cluster ability in under 50 seconds from satellite data arrival at t equals 0 the file lands. The watcher detects it instantly and parallel transfer behinds immediately across all nodes. Mm, current, current verification completes before t equals 50 seconds. This speed is possible because the reactive event-driven model eliminates the idle waiting time that traditional polling systems have built in. Under 50 seconds, fully automated every single time. This solution delivers three major benefits for AEM. Operationally, it eliminated the single point of failure and guarantees scientific continuity even under hardware failure. Um, Financially, the entire system runs on command line hardware on open source software. No expensive proprietary infrastructure required. And at the national level, it is a direct contribution to Mexico's growth as a leading nation in the global space industry. To summarize our technical conclusion, this project achieves zero single points of failure through distributed load across four nodes, double layer security with RAID 50, and CEPH, complete elimination of human error through water automation, autonomous data integrate, via self-healing and current protocols. Um, Full economic viability through open sure implementation community hardware. Looking ahead, the CEPH architecture scaled horizontally by simple adding new nodes with no physical scaling and no redesign required. It runs on open source software, avoiding vendor locking, and it is financially accessible for a public institution like mm, AEM. Um, from a single vulnerable server to a resilient, self-healing distributed ecosystem from AEM is mission ready.